All right, so let me talk about the homework, quote unquote homework. So this was the offending example, and we have these two formulas which seem at odds. On the one hand, we've got x a times x minus y squared, b times y minus z squared, c times z minus x squared, right? But then on the other hand, the spectral expansion, you've got, come on, lambda 1 is 0, lambda 2 times y bar squared, lambda 3 times z bar squared, where lambda 2 and lambda 3 are these rather formidable expressions. And how can we have both of these, and how are they related? Like, what's the coordinate change to get from here to here? Right? And that's a loaded question, because actually there isn't a coordinate change to get from here to here. There can't be. If there was a coordinate change to get from here to here, then Sylvester's theorem would apply. And if Sylvester's theorem applied, then the apparent, then the eigenvalues that are apparently appearing here, A, B, C versus lambda 2, lambda 3, well, they don't match up, right? There's 3 positive eigenvalues here. There's only 2 positive eigenvalues down here. Sylvester's theorem says that for a legitimate coordinate change on a quadratic form, that the spectrum, at least the number of positive and negative eigenvalues, has to stay the same. But it doesn't appear to be the case here, right? So what's the deal? That was essentially the questions that I asked in this quote-unquote homework, right? And so the real loaded question here is to find a matrix P such that P is a basis matrix, and where the quadratic form is that basis matrix, right, where coordinates are the difference, x minus y, y minus z, x minus z. That seems innocent enough, but actually this is what's folly. These formulas right here, x prime equals x minus y prime equals y minus z, and z prime equals x minus z, these do not constitute a coordinate change, at least in the usual sense. Let me show you. So, look, if we think of there being a matrix such that that coordinate change matrix P inverse times x, y, z is equal to this x minus y, y minus z, x minus z. Well, I can rewrite that as this 1 minus 1, 0, 0, 1, 1 minus 1, 1, 0 minus 1 times x, y, z. It stands to reason that P inverse is this, right? But is that a reasonable thing to say? Does there exist a P that's the inverse of P inverse? Sorry, it's unfortunate, my choice of, let's not belabor it anyway. I've made this P inverse, so we're stuck with it. But is that even a reasonable label? Like, is this actually an invertible matrix? Because you shouldn't say something's P inverse if there's no P to invert to get to it, And there isn't, because if you do the standard calculation, like so, when you do it, you get a row of zeros down here, and that means that the inverse does not exist. As of course can also be revealed by just taking the determinant of this alleged coordinate matrix. And you get 0 because the quote-unquote coordinate change corresponding to that difference equation is not really a coordinate change. It's something else. And I don't know the mathematics for that, admittedly, and there's something I need to learn, and I'm not sure what it is. But that's why it's not a fair question. Like, that's not there's no basis to make this happen. It's some sort of like singular transformation or something, and that's part and parcel of why I was confused, because I was wanting this and that to be related in a nice way, and they're just not. They're both nice expressions. This is the expansion by weights. That's so manifestly intuitive in terms of the given graph, right? Like, it's just what that means. It's clear. And the spectral expansion is very useful in terms of calculating things according to associated with a graph, because eigenvalues are so much of the formulas for interesting things we do with graphs. So each of these formulas is very important, and yet they're not related by a coordinate change, because if they were, then the matrix corresponding to these formulas would have to be related by that B transpose AB pattern, and that would force the number of positive eigenvalues to stay the same, the number of zero eigenvalues to stay the same, the number of negative eigenvalues the same by, Sylvester's theorem, right? And it's not the case, right? But that's not a problem because they aren't related as needed to apply Sylvester's theorem, because Sylvester's theorem, remember, says that A be any symmetric matrix, B be any non-singular matrix, then B transpose AB has the same number of positive, negative, and eigenvalues. And this, like, the thing you want to put here, basically P transpose AP, or I guess I have to say P inverse AP, so to speak, in the ring graph example. It's a singular matrix, so all bets are off. Sylvester's theorem doesn't directly apply. And in fact, you can see from the explicit formulas that, in fact, it doesn't apply. There's 3 positive eigenvalues versus having 2 positive eigenvalues. And that's also why it was very important in this example to check that L inverse exists, because that existing means that Sylvester's theorem applies. And that's what gives us that the eigenvalues of M in terms of sign match the eigenvalues of this diagonal matrix over here in terms of the number positive, negative, and zero. And that of course was also then used to prove his plus minus theorem for the weighted path graph, which I didn't actually go through the details of, but so I'm still learning, obviously, and I hope this helps you. And if not, I'm sorry. But you get what you pay for.